Well, when you get started in Physics 2, electricity and magnetism, one of the first things you'll learn about is this equation for the electric field of a point charge. And the idea of this thing is that you've got a charged particle somewhere, let's say a proton as a first example, and you want to know what the electric field is like that it's producing everywhere in space. And so what you're doing with this function is you're saying, I want to pick a point somewhere in space, and I want to know what the electric field is that's caused by this proton there at that location. And what it does is tells you a couple things. First, the r hat, the unit vector over here at the end, tells you that it's always going to point either outward or inward toward the point charge. So in this case, we're working with a positive charge, and so that means it's going to point away from it because r hat always points away from whatever point it is you're looking at. But then the 1 over r squared in the bottom, taking the magnitude of that distance, right? So this distance here is the distance r. The fact that it goes like 1 over that distance squared tells you that it should get weaker the farther away you get. So when you have a relatively close point like our first one, it should be pretty strong. But when you have a point that's farther away, like this second one here, it should be weaker. So you notice it's going to have a different magnitude and a different direction. It's going to have a different magnitude because it's farther away. It's going to have a different direction because it's at a different angle. So you'd have a bigger E up here, you'd have a smaller E down here, and they would point in different directions. The story changes a little bit when you work with a negative charge. So when you work with an electron over on this side, the main difference is going to be with the Q value, the charge there. Instead of being positive, that Q is going to be negative, and that means it's going to flip that electric field around. So instead of pointing away from the electron, that electric field is going to point toward the electron. And again, it'll follow the same rule for the magnitude. If you go farther away, then that electric field needs to get weaker. So you have a stronger field closer to the electron. You'll have a weaker field farther away from the electron. And you work out some practice problems with this to get an idea of this scaling, this 1 over r squared, to make sure you understand how the electric field is pointing away from the positive or into the negative. But the next thing you want to start thinking about is what happens when these charges are near each other. What happens when you have two charges? And that's what this video is going to be about. What happens when you want the electric field caused by two charges? Well, it turns out it's probably what you would expect to have happen. The total electric field is going to equal the sum of the electric field caused by each charged particle. So maybe we call this one particle 1, call the electron particle 2. The total electric field is literally just going to be the electric field from the first one plus the electric field from the second one. And that's why we spend so much time practicing getting the electric field from a single charged particle, because when you have multiple charged particles, you're just repeating that process over and over again and then adding the two results that you get. So let's do an example here. Let's suppose we were interested in getting the electric field at, let's say, this point right here that's in between the two particles, a little bit north of their central line there. What you're effectively doing there is trying to get the electric field of each individual particle. So first we want the electric field from the proton. Well, that's going to look something like this. It's going to be relatively moderate strength. It's not too close but not too far from the proton, but it's going to point away from the proton. So that's what E1 is going to look like, E from the proton. Now we need to do the same thing for the E for the electron. Well, it's going to point toward the electron, so it's going to point something like this. And if you pick just the right point in between there, you can actually get these two magnitudes to be equal, because maybe you're just at the right distance to balance them out where the two magnitudes are equal. If we were closer to the proton, E1 would be stronger. If we were closer to the electron, E2 would be stronger. But what I need to do in order to get E total, I need to add these two, right? So it's regular vector addition, like you've done since Physics 1. We take the first vector E1, and then we start drawing after that the second vector E2. And our total is just going to be the tip to tail resultant of that. Our E total is going to look something like this. So there will be a point at which it's perfectly horizontal between the two if I can get those two magnitudes equal to each other. And you can repeat this process for any points in this grid, right? I could pick a point here that is closer to the proton. In that case, my red electric field, if electric fields get color-coded, my E1 is going to be stronger than my E2. My E2 is going to look something like this. Again, it's farther from the electron, so it's weaker, but it's closer to the proton, so the red arrow is stronger. And so again, I do a tip-to-tail addition here. It's not enough to bring it back down horizontally, so my E total is going to look something like this at this point. And I can find another point over on this side, right, where the electric field from the electron is stronger. So we'd have a pretty weak electric field from the proton that's going to be going away from the proton, so it'll look something like this. Here's E1. My E2 is going to look something like this. It's going to look pretty strong. So if I put that tip to tail with E1, then my total electric field is going to look something like this, E total. And what you end up with is a pattern where these electric fields, they go from the positive into the negative. So the same general rule applies, that electric fields come out of the positive and go into the negative. They're just now following this broader, more nuanced pattern of them all pointing away from positive and going into the negative. Now, that's all well and good to get this nice little picture, but you've seen that it can take you, 10, 15 minutes to calculate one of these electric fields. Now we want to do it for 2 charges and maybe later 4 charges or 10 charges. That's where a computer code comes in really handy. And so what we've done here is set up a Jupyter notebook. Let me zoom in on this just a little bit, where we're setting up our grid. So we're using XList. Oops, where'd it go? There it went. So we're using XList and YList here to set up our grid. We're going to go from -10 to 10 along each axis. -10 to 10 along the x-axis, -10 to 10 along the y-axis. And then we're using NumPy's mesh grid function to set up our grid, to set up our actual grid of points here. We're going to set our electric constant K, 9 times 10 to the 9, and then we're going to bring in a function that we defined in my class earlier this week about a point E field. So this is where you're calculating the electric field due to a point charge. And so in order to do that, we need to have a charge, and we need to have the location of the field that you want, X field and Y field. So the item here, this charge, this is something called a dictionary. A dictionary in Python is a collection of several quantities. What we're going to do down here is define our dictionaries using the little curly brace notation. When you want to make a dictionary in Python, you just put it inside little curly braces, and you put down the names of the properties you want to keep track of. These names inside the red quotation marks here, they can be anything you want. You can call them Sally, Bob, Fred, whatever you want to call them. Just call them a name that makes sense, right? Don't actually call it Sally unless you're dealing with a quantity that's actually named Sally. We're going to call these quantities Q, X, and Y for the charge, the X location, and the Y location for the charged particle that we're interested in. And so when we do this, we're going to unpack this, call it Q, X charge, and Y charge, just for ease of writing rather than having to write this charge of X every single time. Then we're going to come down here and calculate the distance between the charge and the field point. So this is this R vector that goes in here. We're getting its magnitude using the Pythagorean theorem. We're taking basically this X value going across here. We're taking this Y value going up here, and we're getting this center to center distance for the magnitude of R as just square root x squared plus y squared. You can extend this to 3D if you want, but it's just easier to put everything in 2D for the sake of graphing it and visualizing it. But if you needed to do 3D, you could just tack on a plus z squared there inside the square root. No real big deal. It just keeps extending to however many dimensions you are working in. And so that's what we're doing here. We're taking that x distance squared plus the y distance squared all inside of a square root. Then we're going to calculate the magnitude of the charge, taking kq over r squared. Now, I'm using a little bit of a trick here because this is technically not the magnitude because this charge could be positive or negative, but we're going to use that to our advantage because if I have a negative magnitude here, a thing I'm really not allowed to do mathematically, I'm encoding that here in the Python so that it will flip around the direction of the electric field for a negative charge. So I'm sort of compiling some extra information in there. Then down here we calculate the angle that the electric field is going to make. So when we say angle here, we've used Pythagorean theorem to get the magnitude here for r. Now I need to get the angle in here measured from the positive x-axis. And so if you work out a little trig here, you can tell that theta is going to equal the arctangent of the opposite over the adjacent. And as long as I'm consistent in making x horizontal and y vertical, positive being the right direction and positive being the up direction, then I'm going to be able to encode that theta in any value 0 to 360 as I need, or 0 to 2 pi because it's going to use radians. And for that, we're going to use the arctan2 function. The arctan function works fine except when you get to 90 degrees where the tangent goes off to infinity. This thing handles the infinity a lot better. And so we just take the y and the x as our two arguments there. And then what we do, we're going to get the components of the electric field. That's just going to be E magnitude cos theta, E magnitude sine theta. And so by running this, I'm defining this function. I'm saying here is the function I want to use, that when I have a charge and a location for the field, I can put that information in and get out the electric field. And what I hope you notice if you've done this in class is that this looks exactly like what you do in class, right? You figure out what this distance is, you figure out what your angle is, and then you figure out what your components are to build the electric field vector. It's exactly what you do in class. We're just handing it off to the computer to do the actual number crunching for us. All right, so with that defined, we need to start setting up our charges. I'm setting up a scenario here where I've got one charge particle of Q1, one charge particle of Q -1. What I'm doing here is setting up multiple dictionaries. So I've got one dictionary here, I've got another dictionary here, and by separating them by a comma, I'm creating a list of dictionaries. I'm saying I want charge 1, charge 2, charge 3, charge 4, however many you want. You could keep adding curly braces to add more charges. Now we're giving them each a location. So this positive charge is going to be on the negative side of the y-axis. This negative charge is going to be on the positive charge of the positive side of the y-axis. Too many positives and negatives flying around at 11 o'clock in the morning. And then we need to define a new function because I want to be able to take the electric field from each of these point charges and add them together. So this new function E field, not point E field anymore, but E field, brings in this entire list of charges to then calculate the total field at x field comma y field. So what we're doing here, we're saying I want you to take this field, right? I want you to take point E field here. That's going to return your contribution to the EX and your contribution to the EY, and we're going to add that onto EX and EY. So we're using a little bit of Python shortcuts here, nothing to really be frightened of. This plus equals, it looks really funny mathematically. But in Python speak, it just means add to. So it means take this new EX and add it to EX. So if your EX was 0 before, now it's going to equal new EX. And if it equaled new EX before, we're going to add the new EX to it as you loop over all the charges in the list of charges there. So let's run this to get both of those defined. And now it's time to make the thing. So this is a pretty versatile graphing function here. This is called a quiver plot. Quiver is just a way of making arrows on a grid. And so the grid locations are given by x comma y. So x comma y here is specifying the locations of where to place the arrows, and then ex and ey are specifying the horizontal and vertical components for their arrows. So it's a location and two components. That's exactly what we're doing with this E vector here. You're specifying a location with r and then two components, ex and ey. And they don't have a 3D version of this. That's why we're working in 2D for this one. So let's run this. Let's get our electric fields. And there you have it. There's what the electric field looks like for these two point charges, two charged particles with equal but opposite charges, same magnitude but opposite sign, located a nice distance from each other. And it looks a lot like what we were starting to draw over here, right? Arrows going from the positive into the negative. I did 3 of them. Python here has done, 10 by 10 of them has done Is that 100? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Excuse me, it's done 20 by 20 of them. So it's done 400. Hold on. Brian, don't do math in your head on YouTube. Yeah, 400 of them. 400 of them. So that's really cool. That gives you an idea of what this looks like. We call this a dipole because it's got two charges of equal magnitude but opposite sign located opposite of each other. And you get this really cool dipole pattern here.